Okay, so up to the last class we were talking about different mechanisms of creep and how you can identify the stress and temperature window where one particular mechanism of creep would be dominant over others and things like that. So, now we are going to talk about creep testing methods. So, all the analysis required for the analysis of data you need creep data, and how do you generate the creep data. So, what we will be talking in this lecture is I will introduce you to certain creep testing methods. So, the well known creep testing methods are listed here. So, the creep testing can be carried out under tension or it can be carried out under compression. You could also carry out creep testing in the flexural mode, and there are also certain creep testing methods which involve stress rupture under internal pressurization. So, if you have a tube of which you want to study the creep behavior, you can internally pressurize the tube with some inert gas and study the change in dimensions as a function of time. And we could also there are other small scale creep testing methods such as impression creep, which are also in existence, and people regularly use these as alternates to the conventional creep testing methods. So, in this particular lecture we will be talking about tensile and compression creep testing methods and briefly about flexural, and then I will introduce you to one of the small scale creep testing methods, which is the impression creep method. Now, coming to tensile or compression creep testing methods. So, these are the types of load frames that you can use for carrying out tensile or compression creep testing. So, you could use the direct load creep testing method. So, for example, in the direct load creep testing method, what you can do is you can take your sample and apply the load that you are interested in directly onto the sample. So, the load of, say, if you want to do your test as 100 newtons, then you directly apply 100 newtons to your sample. Whereas, in the lever arm creep testing method, the load is not directly applied, it is transmitted through a lever arm. So, what the lever arm does is there is so say this is your arrangement, there is a point, fulcrum point, and then you apply the load here, and then the load gets transmitted through the moments onto the sample, and usually the load that eventually gets applied on the sample is an amplification of the applied load, that is because of the balance of moment. So, you have a moment acting on the right arm of the lever, and then you also have a moment acting on the left side of the fulcrum, and that based on balancing of moments, the load that is applied is eventually amplified and transmitted to the sample. So, these are the two approaches that that have been developed. You can have a direct load creep testing method, or you have a lever arm creep testing method. The creep testing methods. So, there are many standard creep testing methods. I have listed down here two of them here. One is the ASTM E139, which is a standard test methods for conducting creep rupture and stress rupture for metallic materials. And for ceramics, you could have creep and creep rupture of continuous fiber reinforced advanced ceramics under tensile loading at elevated temperatures. So, for that the standard is C1337-10. So, there are a few others as well, but here I am listing only these two for you to know the type of standards that are available. And in the next set of slides I will be talking briefly about the ASTM E139. So, so when you want to carry out a creep test, the basic requirements that the creep testing machine should have is, one, you should have a frame or a load frame on which you can load your sample, and then you need a specimen fixture to hold the sample or to hold the specimen. And then, since creep is a high temperature test, so typically you need a high temperature furnace, the furnace which can provide you the temperature of interest, the test temperature that you are interested in. Then you also need some extensometers in order to measure the strain that is getting that the sample is experiencing, or the sample is exhibiting, the plastic strain that should be measured by the extensometer. And the latest creep machines also have softwares which allow you to monitor the deformation continuously, and some of them are also capable of analyzing the data generated. So, say if you are generating a strain versus time curve, and then the softwares are also capable of analyzing the data and giving you the strain rate of deformation, things like that. And like I mentioned earlier, the loading can be direct or can be transmitted to the sample by using a lever arm. So, coming to creep testing, creep test a creep test is basically a test that allows the measurement of creep and creep rates at applied stresses below what would have caused fracture during the time period of the testing. So, what this definition, this is the ASTM E139 definition, what it tells is that the creep test is a test where you are not taking your sample to fracture. So, you are here in this particular type of test, your focus is only on measuring the amount of deformation that the material undergoes in a certain time period of testing, and typically the test is carried out only to a few percent of plastic deformation. So, the maximum deformation that is allowed in this kind of a test is only a few percent, and hence the measurement of the strain, the measurement of the plastic strain requires the use of a sensitive extensometer. Now, the creep test, the advantage of the creep test is that it helps understand the load carrying ability of the material for limited strains. So, I will explain what I mean by the load carrying ability. Now, in contrast to the creep test, a creep rupture test is one where the deformation is carried out until rupture. So, a creep rupture test is a test in which progressive creep deformation and time to rupture both are measured. So, you are measuring both the deformation as well as the time to rupture, and here the plastic deformation that the sample experiences is a lot higher than that developed during a regular creep test, because here you are taking your sample till rupture. So, the amount of deformation that the material experiences is significantly higher. And a variant of the creep rupture test is the stress rupture test, and in this type of a test, here the only measurement is the time to rupture. So, a stress rupture test is a test in which time for rupture is measured and no deformation measurements are made during the test. So, if you see, there are three things that are coming out. You have a creep test, then you have a creep rupture test, and then finally you have a stress rupture test. In the creep test, you are only measuring deformation up to a few percent. So, a few percent plastic strain is what you are measuring, and you are measuring the time taken to reach that few percent of plastic strain. In the creep rupture test, you are allowing the test to run until rupture, and during the test you are measuring both the plastic deformation and then you are also measuring the time taken to rupture. But in the stress rupture test, what you are basically doing is you are only measuring the time for rupture, and you are not providing any information or gathering any information on the plastic deformation experienced by the material during the test. Now, the rupture tests, that is both the creep and the stress rupture test, they allow you to understand the ultimate load carrying ability of the material as a function of time. So, what I am trying to say here is, unlike the creep test, so the creep test basically is carried out up to a few percent. So, say this is epsilon and epsilon versus time. So, if you define your creep test as time taken to a certain strain, let us say 5%, and you have already defined the time, say you are saying the time is 100 hours and the maximum allowable strain is 5%, then basically based on that you can know what is the maximum load that you can apply. So, if you define the time for which you are going to allow the material to strain and the maximum strain that you are allowing is only 5% as an example, then you know what kind of loads you can apply. That means you know what is the load carrying ability of the material. And in the second case, and if you have defined the sample up to rupture, and if you are saying that the time to rupture, let us say it is 1000 hours, and you are saying you want a time to rupture of 1000 hours, then again you know how much is the maximum stress that the material can take, so that it provides you at least a time of 1000 hours. So, here if your load exceeds P max, then your time to rupture will become less than 1000 hours. So, P max is the maximum load that the material can take, so that it provides you a time to rupture of 1000 hours. So, if you look at both these plots, these together can tell you the entire behavior or the entire load carrying ability of the material. If you are defining the strain that you are allowing and the time to reach that strain, then you know what kind of loads you want the material to experience. But if you are defining the time to rupture and then accordingly, and you know what is the maximum load that the material can experience. So, basically the creep and the rupture tests together help understand the load carrying ability of the material, and hence they are complementary to each other. And the type of test that you are going to choose depends on the service usefulness defined for a given material. For example, if the time to failure is the limiting criterion, then rupture test is chosen. However, if time to a certain plastic strain is the limiting criterion, then a creep test is chosen. So, for example, if you are looking at the gas turbine blade, say you have a gas turbine blade and it is enclosed in a casing, and here you know even a strain of say few percent, like let us say 2 or 3% is going to cause the gas turbine blade to hit the casing, which means that the engine is going to get damaged. In that case, you are going to choose a creep test, because all that you are interested in is knowing what is the time taken to reach 2% plastic strain. So, in such a case you may want to go for a creep test. However, in other cases, say if you are talking about a tubing for disposal of nuclear waste. So, if you are looking at tubing for disposal of nuclear waste, here your main concern is when is the tube going to rupture, and if it ruptures, it is going to allow the nuclear waste to come in contact with soil and other environment, which means there are environmental hazards possible if the tube ruptures. So, in this condition probably your interest is to know what is the time to rupture for a certain applied load. So, based on your end application you can decide which particular type of test you want to adopt. Now, when you are doing your creep test, so now once you know that you have once you know the type of test that you are planning on doing, then what becomes important is the actual creep test. So, here when you are doing your creep test and you have a creep testing machine, you have to ensure that your creep testing machine will be erected in a place which is free from vibration and shock due to external causes. So, if your creep testing machine is located in a place where vibrations and shocks from external factors are regular, then your data is going to get influenced by those factors. So, essentially your testing machine should be isolated from external vibration and shocks, because vibration and shock will introduce noise in the strain time curve. So, if you have strain versus time, you want as smooth a curve as possible so that you can analyze your data better, but if there is a lot of noise, then probably you will see a lot of variation or fluctuation in your measurements, and this will prevent analysis of your data. This will interfere with good analysis of your data. So, that is why you want to reduce the amount of noise that is generated in your strain time curve. However, if there are vibration effects which you cannot avoid, then one of the specifications provided by the ASTM is that the noise should not exceed 7.5% of the total plastic strain. So, if vibration is unavoidable, then probably, and if you have to live with it, then the maximum vibration maximum effect brought about by the vibration should not exceed 7.5% of the total plastic strain, and the external vibrations should also not introduce any force variations greater than 1% of the applied force. So, if you are applying a certain force and you do not want the external vibrations to make their own contributions to the applied force, and in case these contributions are unavoidable, then the maximum that you are going to allow is only 1% of the applied force. The other precautions that you should exercise are as follows. You should exercise precaution to ensure that the applied force on the specimen is as axial as possible. So, if you are doing your tensile or compression test, the load that is getting applied should be as axial as possible. So, the load should be as axial as possible. Sometimes perfect axiality is difficult because the pull rods and extensometers pass through the packing at the ends of the furnace. So, say this is your sample and then you have a furnace around your sample. So, your sample is inside the furnace and then this is connected to a pull rod. So, this is connected to a pull rod. So, you are for the sake of insulation you are going to pack some materials around the pull rod, so that the heat losses that the sample and the pull rods experience is minimized. So, when you are applying when you are including some packing material around the furnace or at the entrance or the exit of the pull rod, these packing material could also lead to some kind of disturbance or misalignment, and so this can create issues with axiality. So, if such a case is there, then the bending strains due to the sample loading etc., which have to be avoided, and even if it is unavoidable, then the maximum bending strain due to grips, extensometer etc., should be maximum allowed bending strain is 10% of the axial strain. So, if a loss of axiality is unavoidable and if the loss of axiality leads to some amount of bending strains, the maximum bending strain that the creep test or the ASTM standard allows is only 10% of the axial strain, and the machine should be evaluated for axiality by tests at room temperature with specimen dimensions and geometry similar to the actual specimen dimension and geometry. So, before you carry out your test, you should also evaluate your machine for axiality, and what you can do is you can create some dummy samples, but these samples should have dimensions and geometry similar to the actual sample, and using these dummy samples and by testing at room temperature you can find out the amount of non-axiality that your sample is experiencing. Also, important thing to note is that the gripping devices and pull rods generally tend to oxidize, warp and creep with repeated use at elevated temperatures, and when they start deforming or start losing the geometry or warping etc., this can also lead to bending stresses, and so the grips and pull rods should be periodically evaluated and retested for axiality and reworked if necessary. Now, one of the important components of your creep test is the heating apparatus or the furnace. Now, because creep is a high temperature test and the data generated is dependent on the temperature at which you are testing. So, it is quite clear that if your temperature is higher, the strain rate of deformation will be higher and your time to failure will also change. So, T1, T2, if T1 is greater than T2, your strain rate epsilon dot 1 is going to be greater than epsilon dot 2. So, the temperature has an important role to play. So, the heating apparatus must maintain temperature within certain limits. So, say if your test temperature is T test and you are carrying out your test at temperatures lower than 1000 degree centigrade, then the maximum variation the maximum variation of the sample temperature is 2 degrees. So, if your T test as an example is 900 degree centigrade, then your sample temperature should not be great, maximum allowed is 900 degree centigrade plus minus 2 degree centigrade. So, your sample temperature should be in that range. Similarly, if your T test is greater than 1000 degree centigrade, let us say T test is 1100 degree centigrade, then here your maximum variability is allowed variability is only 3 degree centigrade. Also, the heating should be carried out by an electric furnace or radiation furnace, and the sample with the sample tested in air unless other media is specifically desired. So, typically the tests are carried out in normal environment in air environment unless other media such as argon or oxygen etc., has been specifically mentioned for the test. And the thermocouples used for temperature measurement must be calibrated regularly, because the thermocouples will tell you what is the sample temperature. So, if there is an error in the measurement by the thermocouple, then that could also lead to a faulty creep test. So, the thermocouple should be regularly calibrated. Also, when you are going to do your creep test, it is desirable to stabilize the sample at 5 to 20 degree centigrade below the desired temperature before making the final adjustment. So, what here I am trying to say is, if your test temperature is 900 degree centigrade, then first you should stabilize your sample at maybe 880 to 895 degree centigrade. So, you can stabilize your sample in this temperature range and then make your final adjustments, so that your test the sample temperature reaches 900 degree centigrade. The advantage of this approach is, in case you are trying to stabilize your sample directly at 900, then there is always a possibility of overshooting. So, the furnace may end up overshooting and providing temperature greater than 900 degree centigrade, and since some phase transformations can happen at higher temperatures. So, that is why it is always better to stabilize your furnace at lower temperatures, slightly lower temperatures, and then make the final adjustments, so that the sample temperature does not overshoot your test temperature. Also, the time of holding at a temperature before starting a test must not be less than 1 hour. So, basically if you are doing your test at 900 degree centigrade, after you reach 900 degree centigrade, hold the sample at that temperature for at least 1 hour, and then only you start your test. And any variation in temperature from the set temperature can lead to change in creep rates, and hence in such cases the test results can be discarded. And here the operator or the person carrying out the test or the person interested in the data should use his or her judgment to decide based on the time duration for which the variation was observed. So, if there is a variation in your test temperature, then you will have to use your judgment on deciding whether the data should be used or the data should be discarded, and of course, your point of judgment is based on the time duration for which the variation was observed.